In this video, we're going to talk about Unit 12.1, which is on vectors. So the idea is some quantities that we talk about and represent in math can easily be represented by just ordinary numbers. These include things like time, temperature, distance, area, and so on. Other quantities need more than just a number representation. They sometimes need a magnitude, that is, how strong or powerful is it, and then secondly, they also need a direction. In what direction is that thing being pointed? So commonly used quantities that we represent using vectors include things like force, velocity, and acceleration. So these are the things we want to develop the tools to be able to work with. A lot of this has applications to physics if you are in or going to take physics, and also in any kind of engineering field, you will talk about these and use these quite a bit as well. So what we need to do is we're going to have to get familiar with some new vocabulary and symbolism and become familiar with that. So that's where we're going to start right now. We are going to say a vector, and I'm going to represent this vector PQ. So I'm going to write capital P, capital Q. I'm going to draw, sometimes it'll just be kind of like a half arrowhead on one end. Sort of looks like a ray symbol from your geometry days. So it can be represented just with that half arrowhead, sometimes with both. Doesn't really much matter. But what that indicates is that vector, vector PQ, starts at the point P and ends at the point Q. And so we call P then the initial point. That's where the vector starts, the initial point, and point Q, where the vector ends, is referred to as the terminal point. So a vector, you might represent it something like this with the arrow, and this would be the point P, where it starts, and at the end of that arrow is a point Q. So you can see that the order you write these in matters. So the vector PQ is not the same as the vector QP because they point in different directions. So we will talk about the magnitude of a vector. So we represent it visually. The magnitude of the vector is going to be its length. The magnitude, I'm going to say, of vector PQ is its length. And the symbolism we use for this, different books use different symbols, so there's a couple different ones. Our book is going to write it, it looks kind of like a double bar absolute value sign. And so that symbolism right there represents the magnitude or length of vector PQ. Some other books, you will also see it written just like an absolute value sign. So if you see that somewhere else, don't be confused by it. They mean the same thing. They're referencing the length of that vector. Now, we will talk about the direction of the vector. Initially here, we will start out by talking about the direction of vector PQ as its slope. As if that's a rise over run, but very soon we will get to, not today, but eventually we will get to, so I'm going to say ... We're going to talk about a direction angle. And so that is going to look very much like what we've been doing in our trig stuff. But I'm getting ahead of myself a little bit there. Two vectors are equivalent if they have the same magnitude and the same direction. Two vectors are equivalent if they have the same magnitude and direction. So let me give you an example, and we'll try to show that two vectors are equivalent. So I'm going to go to a new panel here. So consider, I'm going to draw an XY axis here, and I'm going to go, let's go 1, 2, 3, 4, 1, 2, 3, 4. So I'm going to pick the vector RS. So I'm going to start at the point 1, 2, and call that point R. And then I'm going to go up to 4, 4, and that's going to be the point S. So this is our vector RS. On the same XY axis, I'm going to draw the vector PQ. So I'm going to put P right here at the origin, and I'm going to go over 3 and up 2, and I'm going to call this the point Q. So there is our vector PQ. And if I did this right, they should, and you may have to use your imagination a bit, we think oftentimes as vectors as being slidable. That is, you can move them around in the plane. So two vectors are going to be equivalent to each other. The vectors PQ and RS will be equivalent to each other if they have the same length, that is magnitude and direction. So you could also think of it visually as if you slid this vector over, and if it laid right on top of vector PQ, if they're equivalent, they're going to be the same same length, and they'll be tilted the same way, the same direction. So what we're going to look for is we're going to find what's called the component form of RS. So to find the component form of RS, we're going to write it in what's called component form. So we're going to write these kind of pointy parentheses. Those are actually called angle brackets, but you don't hear that said very often. And we're going to find what is known as, sometimes called the X component and the Y component, or the horizontal component and the vertical component. So to do that, we use the idea of tip minus tail. So if we look at the point R, and its coordinates are given by 1, 2, and Q has the coordinates, I believe, 4, 4, then to get the component form of vector RS, we go tip minus tail. That is, we take the X component, or horizontal component, of I called that Q, it should be an S, sorry about that. Let me try that again. Then we're going to go 4 minus the 1, and then we'll take the 4, that's the Y coordinate of S, minus 2, the X coordinate of R, and so that becomes 3, 2. So that's the component form of vector RS. And that shows you also, if you put it in what's called standard position. So standard position is as if we wrote the vector where its initial point is at the origin. So if we move the R to this point at the origin, and we can see we will go in the X direction 3 and in the Y direction 2, then this is the standard position of vector RS, the standard position representation. So we can see then that the magnitude of vector RS is going to be its length, but you can see that's really just Pythagorean, it's the Pythagorean theorem. So if you're imagining making this a right triangle, then the 3 is going to be that length of that horizontal side there, and the 2 is going to be the length of that vertical side. And so to find magnitude, we're going to get the square root of 3 squared plus 2 squared, and that's 9 plus 4. So we get the square root of 13 is the magnitude. Now, similarly, you can see that vector PQ, vector P, if I can get my pen back up, PQ it's already in standard position, and so you can see that its component form is going to be 3, 2. So at this point we can see that these are equal to each other, but to demonstrate that, we'll say that the magnitude of PQ is going to again be the square root of 3 squared plus 2 squared, which is the square root of 13. So we have showed that they have the same magnitude, and we need to argue that they have the same direction. And we, for today, or at least early on, we'll consider direction just by the slope of the line containing that vector. So if we look at our vector RS, and we can see that it's going to rise 2 and run 3, so that's going to make the slope be 2/3. And similarly, the slope of our vector RS, or PQ rather, is also going to be 2/3. So because they have the same direction and they have the same slope, we would say that PQ and RS are equivalent to each other. Okay, so let me get a new panel up here. We also have an idea of what's called a unit vector. So a unit vector is a vector of length 1. So it's 1 unit long, is a vector of length 1. And we have the idea also of a 0 vector. So a 0 vector, which we will denote as 0 with that vector symbol over it, and that is the vector given by 0, 0. And you can see that the magnitude of the 0 vector is 0. It's really just a point. It's just a dot. Okay, so let's see if we can use this idea of the component form. So if I give you a point A that's given by, say, 4, comma, -7, and point B that's given by -1, comma, 5, then can we find what is vector AB, and then we'll find what is its magnitude. So using the tip minus tail rule, we're starting at A and going to B, so we'll take the ending x value, -1, minus the beginning one. This is our tip minus tail. And then we'll take the ending y value minus the beginning y value. And so our vector AB is going to have horizontal component of -5, and that was a -7 there. So that's going to be a +12. So there is our vector AB. The magnitude of vector AB is going to be the length of that, so we will just use the Pythagorean theorem using our horizontal and vertical components as the two sides. So that's going to be 25 plus 144, and in this carefully constructed problem, that's going to be 169, which is 13. So the magnitude of vector AB is 13. Now we have some vector operations. I'm going to move to a new panel here. So we have certain operations we can do with vectors. So the first we're going to refer to as what's called scalar multiplication. So now we have these different quantities. We have ordinary numbers, things like -1, 3, 2/3, square root of 5, pi, so on. These are ordinary numbers we're going to refer to as scalars. So they don't come with any other special notation. We have vectors, which are going to now look sort of like ordered pairs, except that they're going to have these angle brackets. So they might be something like 1, -2. We might represent a vector with 2 capital letters, like you would have in your maybe geometry days, looking a lot like a ray. Sometimes we will do it with a single letter, put that symbol, and call it vector V. So these are the different notations. So scalar multiplication refers to when we take an ordinary number k and then times a vector, say pq. And so if we have, say, pq, I'm just going to come up with this vector and say it's going to be, say, 3, -5. Then we can do scalar multiplication might be something like 2 times the vector pq, which means we're going to multiply both of the components by 2. And so that would create a new vector, which would be 6, whoops, not a negative, come on, pen, 6, comma, -10. So that is the vector 2 times pq. The -1 times pq, or negative of pq, is going to change the signs of those components. And so if you were drawing that, pq and negative pq would point in opposite directions. We can do something like 1/2 times pq, and so we would again get 1/2 times 3 is 3/2, and 1/2 times -5 is -5/2. We can do what's known as vector addition and subtraction. So vector addition is how we add two vectors. So suppose I say u is the vector given by 2, 3, and v, I know this is maybe bad choice of letters. U and v are oftentimes hard to distinguish in the way we write them, but these are commonly used in vectors as u and v. So I'm going to say vector v is going to be -1, 5. Then we can say a new vector, we can create a new vector, u plus v, and it's just what you would like. You're going to add their components. So 2 plus the -1 and 3 plus the 5. So adding two vectors creates a new vector, say 1, 8, which is the sum of those two vectors. And likewise, we can create a vector, say u minus v, by subtracting their components. So we would take then 2 minus the -1, 3 minus the 5. And so the vector u minus v would be 3, -2. Now there is a picture that goes with this. So I'm going to go to a new screen and talk about what is sometimes referred to as the parallelogram rule. The parallelogram rule, and this is for adding and subtracting vectors. So I'm going to give you a visual here, and this will also bring into mind or reinforce this idea that these vectors are slidable. So suppose I just say here is a vector, I'm going to say u, and I'm just going to make it easier to visualize, I'm going to draw it right along the x-axis, and then I'm going to come up with a new vector, and I'm going to change my color. So I'm going to say right here is vector v. So when we put vector u and v in standard position, that is where no matter where they may have come up, we're going to move them so their initial point is going to be right there at the origin. Then they will create a parallelogram. So I'm going to extend those and form a parallelogram. So the parallelogram rule says if we want to, I'm going to change colors here for a minute, and I'm going to say if we want vector u plus vector v, then I'm going to move those vectors so they go tip to tail. So I'm going to slide this vector u and move it up here, and my claim is this vector is also a copy of u. And so it is the same length as the vector u down below here on the x-axis, and is pointing in the same direction. So once they are tip to tail here, then the vector u plus v is going to be the vector we get by starting at the initial point of the first vector and going all the way to connecting it to the endpoint, the tail of the second vector. So this diagonal that I have just drawn there is the vector u plus v. Sometimes that's referred to as a resultant. We'll come back to that much later. But when you add two vectors, the new vector that is created is known as a resultant. Okay, now let's look and see if we can do, let's do, say, the vector, let's do u minus v. So now we're going to do a subtraction. So I'm going to look at this copy of u right here. So that's the same length and direction as my original blue one. Then I'm going to take this, this vector v, and I'm going to multiply it by -1, which is going to change its direction. It's still going to be the same length, but it's going to go in the opposite direction. And then I'm going to slide that so that it comes over here. So this is now negative v that I have moved so that it is tip to tail with vector u. And so now what I can do is, starting at the beginning of this copy of u and kind of traversing it from u all the way through negative v, where it ends up with is going to be the vector u minus v. So what I have drawn there in the yellow is that vector u minus v. So what we see from the parallelogram rule is if you take two vectors and you write them in standard position, one of the vectors is going to be the sum of those two vectors, and the other diagonal, I'm sorry, one diagonal is the sum, and the other diagonal is the difference, the subtraction of those two vectors. Okay, a few quick properties. Hopefully some of these will seem pretty intuitive. These are some properties of vectors. And so we have one of them is that the vector u plus the vector v is the same if you reverse the order. It's the same as vector v plus u. So no big surprise there. That's known as a commutative property. And also the order that you add three vectors does not matter. So if I want to add three vectors and I add the first two together first, I'll get the same thing as if I added the second two together first, or whatever order we wanted. So the order that you add vectors doesn't matter. The zero vector has the property that when you add the zero vector, remember that's 0, 0, to any other vector, you just get the same vector back. Another is that there is an inverse property of addition. Any vector has an opposite, and when you add a vector to its opposite, you get the zero vector. Another is if you multiply one scalar times a vector, it's the same as if you multiplied those two scalars together first and then multiplied that by the vector. I don't think that's too surprising. A sixth one is that you can distribute a vector over the addition of two scalars. I don't think that's too big of a stretch either. In a similar fashion, you can distribute a scalar over the addition of two vectors. So that scalar would just multiply each of the two vectors, and then if you wanted, you could later add them. The number 1, that scalar 1 times any vector just gives you back that same vector. And likewise, 0 times any vector gives you the 0 vector. And this may or may not be believable, but the magnitude of a constant times a vector is going to be that constant times the magnitude of that vector. Okay, see what that will do for homework number 50 for you.